Welcome. So in this video we will do some of the numericals on preparation of buffers. So first numerical is on acetate buffer. So the question is, how much glacial acetic acid and sodium acetate are required to prepare 250 ml of 0.1 molar buffer at pH 4.8. Now we are given pKa of acetic acid as 4.75, acetic acid molecular weight 60, sodium acetate molecular weight 82, density of glacial acetic acid is given as 1.049 gram per ml. So in the end we will have answer like this. We have to use 0.675 ml glacial acetic acid and 1.08 gram sodium acetate, and we have to make up the volume in a 250 ml volumetric flask. We will have buffer of 0.1 molarity at pH 4.8. okay, so at the end we must arrive at this answer. Okay, let's start. So always when we perform buffer calculations, we make use of an equation which is known as the Henderson-Hasselbalch equation. So it is equal to pH equal to, it is given by pH equal to pKa plus log of salt by acid, or we can say that it is conjugated base by acid. Okay, now pH is given as 4.8, pKa is given as, that is of weak acid, that is acetic acid, is given as 4.75 plus log of salt by acid, and from this we will have A minus divided by HA is equal to 10 power, that is 4.8 minus 4.75 is equal to 0.05, that is 10 power 0.005 is equal to 1.12. okay, now let us say that the concentration of HA is X, that is here our HA is acetic acid, and the acetate ion or sodium acetate will be, then it will be equal to 1.12x, as here it's given that say it is X, so it will be 1.12x. now total is 0.1 molar, so 1.12x plus x is equal to 0.1, and from this we will have x equal to 0.0472 molar, and since x is equal to 0.0472 molar, your A minus will be equal to 0.1 minus 0.0472, that is equal to 0.0528 molar. okay, now we have molarity. In molarity, the concentration of acetic acid and acetate ion, and we have to prepare 250 ml, that is 0.25 liter we have to prepare. So how much moles of acetic acid will be required and how much mole of sodium acetate will be required, that we want to know now. So as we know that molarity is equal to number of moles of solute present in 1 liter of solution. okay, now say it is given, we here 250 ml we have to prepare, and this is nothing but the number of moles, and from this number of moles will be equal to molarity into your 0.25, that is how much volume we have to prepare in ml, 250 ml, that is or 0.25 liter. So acetic acid number of moles is will be equal to 0.0118 mole, and for acetate ion equal to 0.0132 mole. Now okay, now we have to calculate the actual amount of both, that is sodium acetate and acetic acid to be taken. Since acetic acid is in ml, so we have to calculate its volume, it is liquid, and sodium acetate is solid, so we will calculate in gram. Now for sodium acetate, as it has come here 0.0132 mole into its molecular weight, that is 82, this coming to around 1.08 gram, so we have to take 1.08 gram of sodium acetate. Now for acetic acid, molecular weight is 60, so multiplying by number of moles we have obtained, that 0.0118 is equal to 0.708 gram. Now since density of acetic acid is given as 1.049, so you take volume will be equal to 0.708 divided by 1.049, that's T of acetic acid given to us, and this will be equal to 0.675 ml. Okay, so now we know that we have to take 0.675 ml of acetic acid and 1.08 gram of sodium acetate and make up the volume to 250 ml. Then we must have 250 ml of 0.1 molar acetate buffer at pH 4.8. Okay, so here it's written that we have solved this numerical. Now the final result is we have to take 0.675 ml glacial acetic acid and 1.08 gram sodium acetate, make up the volume to 250 ml. We will have buffer solution of 0.1 molar at pH 4.8. So we have made use of Henderson-Hasselbalch equation in this. And to make it more easier, you can first weigh 1.08 gram sodium acetate, and then you can add glacial acetic acid slightly less than 0.65 ml. Say you are adding 0.650 ml, and then make up the volume to say 250 ml you have to take. So you take initially you make 200 ml, and then we check the pH, and if pH is say less than, so whatever pH is coming, then you have to adjust. Say it is higher pH, then you have to adjust the pH using the remaining glacial acetic acid, that is here remaining will be 25 microliter. So you will add drop by drop till you are having the pH 4.8. Okay, and then make up the volume to 250 ml. In that way you will able to have the exact pH of the buffer. Meaning that in the end instead of fully making up the volume, हम पूरा वॉल्यूम मेकअप ना करते हुए हम इनिशियली जो है कुछ वॉल्यूम छोड़ देते हैं, उसके बाद उसकी पीएच एडजस्टमेंट करते हैं. एडजस्टमेंट के लिए हम ज़्यादातर जो एसिटिक एसिड और सोडियम एसिटेट ही यूज़ करें. अगर हमारा पीएच ज़्यादा है तो हम एसिटिक एसिड का यूज़ करेंगे, पीएच कम है तो हम थोड़ा सा मिलीग्राम में हम सोडियम एसिटेट डालेंगे, तब जाके हमें वॉल्यूम मेकअप करना होता है आपका 250 ml जो रिक्वायर्ड वॉल्यूम. Okay, now let us see the second numerical on the acetate buffer itself. So this numerical, in this numerical, how much glacial acetic acid and sodium acetate are required to prepare here 1 liter of 0.2 molar buffer at pH 4.5. Given things are pKa of acetic acid is equal to 4.75, molar mass acetic acid 60, sodium acetate 82, and density is given as 1.049 gram per ml of the glacial acetic acid. Now in the end we must have the answer. Use 7.32 ml of glacial acetic acid and 5.90 gram of sodium acetate. Make up the volume to 1 liter with distilled water to obtain a 0.2 molar acetate buffer at pH 4.5. So let us see how to arrive at this answer. Now here also we will make use of Henderson-Hasselbalch equation. So pH equal to pKa plus log of salt by acid. 4.5 is pH, 4.75 is pKa. So if we subtract it, it will be minus 0.25, and the salt by acid concentration will be 10 power minus 0.725 is equal to 0.5623. Okay, now if we take HA concentration as X, then your salt concentration will be equal to 0.5623x. Here it is given. Now total is 0.2 molar. Okay, so from this equation we can have the value of X as 0.1280 molar. Okay, so acetic acid molarity required is 0.1280 molar and sodium acetate is 0.0720 molar. Okay, now since the liter number of moles, we can convert it into number of moles. So volume is 1 liter. So simply here your moles will be we will multiply the molarity by the volume, that is 1 liter, that will equal to how much moles, that is 0.1280 moles. And so similarly sodium acetate moles will be 0.0720 into 1 is equal to 0.0720 mole. Okay, now we have to convert them into mass. Okay, so how to convert them into measurable amounts? That for acetic acid we have 0.1280 mole of acetic acid into, that is the molecular weight of acetic acid, which is 60. So this will be equal to 7.68 gram. Okay, so acetic acid, from number of moles we have calculated the gram of acetic acid which is required, that's multiplying by it by molecular weight of the acetic acid. Now since acetic acid is the liquid, so in ml we have to calculate it, so we have to divide it by density, which is equal to 1.049 density, and 7.68 divided by 1.049 is equal to 7.32 ml. And sodium acetate is simple to calculate, 0.0720 into 82 is molecular weight, we will have 5.9 gram. So what answer we have got? 5.9 gram of sodium acetate and 7.3 ml of acetic acid make up the volume to 1 liter, and you will have the acetate buffer of pH 4.5. So here it's written, use 7.32 ml of glacial acetic acid and 5.9 gram of sodium acetate, make up the volume to 1 liter with distilled water to obtain a 0.2 molar acetate buffer at pH 4.5. So in this case also, you initially weigh 5.90 gram of sodium acetate and 7 ml of. So like the previous numerical, in this case also we can take 5.9 gram of sodium acetate and initially add 7 ml of glacial acetic only, and 320 ml, that is microliter, will be used for the for adjusting the pH. So take 5.9 gram of sodium acetate, 7 ml of glacial acetic acid, make up the volume say to around 900 ml, less than the 1 liter, and then you adjust the pH using 320 microliter of glacial acetic acid which is remaining. Till you have pH 4.5, and then volume to be made up with distilled water 1 liter. So that way we are preparing acetate buffer using glacial acetic acid and sodium acetate of 0.1.2 molar concentration. Okay, now let us do another numerical. Now this time we will prepare a basic buffer which is ammonium hydroxide buffer. So the numerical is, prepare 500 ml of 0.1 molar buffer solution of pH 9.25 using ammonium hydroxide and ammonium chloride. So here pK of ammonium chloride, that is given as 9.25, and molar mass of ammonium chloride is given as 53.5 gram per mole. Concentrated ammonium hydroxide solution is given to us 25% weight by weight. Density is 0.91 gram per ml. Molar mass is equal to 35 gram per mole. Okay, so how to solve this numerical? At the end we must have the answer 1.34 gram ammonium chloride to be taken and 3.85 ml of 25% ammonium hydroxide solution to be taken. You make up the volume to 500 ml to obtain a buffer solution of pH 9.25 of strength of 0.1 molar. Okay, so let us see how to arrive at this answer. Okay, so using Henderson-Hasselbalch equation, so here it is because we have a basic buffer. So here equation will be pH equal to pKa plus log of base divided by, here base, your base is ammonium hydroxide, divided by its conjugate acid, so that will be equal to ammonium chloride. Okay, so base by acid. Now pH equal to 9.25, your pK is 9.25, both are equal, so therefore concentration of base and acid will also be equal. Okay, so since total concentration is 0.1 molar, so each will be of 0.05 molar. This is now clear, each will be of 0.05 molar. Now since we have to prepare 500 ml, that is 0.5 liter, moles of ammonium hydroxide that are required here is 0.05 into 0.5 is equal to 0.025, so each required is of 0.025. so here also the same way, WB by MB into 1000 by V, the molarity definition. So we are given molarity each of 0.05. So here we can calculate number of moles, and since V is given as 500 ml, so we will put here 500 ml and we will have 0.5. So here 0.5 into 0.05 is equal to 0.025. Here number of moles of ammonium chloride is 0.025 mole. Now we convert it to mass because ammonium chloride is solid. We will have 0.025 into its molecular weight, which is 53.5, is equal to 1.34 gram. Okay, so molecular weight of ammonium chloride is 53.5. Is multiplied by number of moles, we will have the amount of ammonium chloride required. Now coming to ammonium hydroxide, so solution given is 25% weight by weight, density is 0.91 gram per ml. So mass of ammonium hydroxide which is required here is 0.025 into 35 gram per mole is equal to 0.875 gram. Okay, so how much mass is required? That is 0.025 into molecular weight of ammonium hydroxide, which is 35, is equal to 0.875 gram. Now since this is in liquid and we are given liquid of 25% solution, that is concentration, meaning that 25 gram ammonium hydroxide is present in 100 gram of solution. And if you want to take how much solution to be taken, if you want to have 0.875 gram, that is 100 by 25 into 0.875 is equal to 3.5 gram. Now since the density of ammonium hydroxide solution is given at 0.91 gram per ml, so volume equal to 3.5 divided by 0.91 gram per ml is equal to 3.85 ml of ammonium hydroxide solution, 25% weight by weight. Okay, so this is your answer, that you have to take 1.34 gram ammonium chloride and 3.85 ml of ammonium hydroxide solution, make up the volume to 500 ml to obtain a buffer of pH 9.25 and 1 molar 0.1 molar strength. In this case also, you take whole of the amount of ammonium chloride and take slightly less of 25% ammonium hydroxide solution. Say you are taking 3.50 and remaining here in this case will be 25. Here it is 35, 350 microliter remaining will be there, and that will be used to adjust it the pH at the end. So instead of making 400 ml, say you are preparing initially 400 ml and then use ammonium hydroxide solution to adjust the pH to 9.25 and finally make up the volume to 500 ml, you will have buffer solution, ammonium hydroxide buffer of strength 0.1 molar. Okay, so in this way we are preparing the buffer solutions. Okay, now let us see another numerical on ammonium hydroxide buffer. In this we have to prepare 250 ml of 0.1 molar buffer at pH 9 using ammonium hydroxide and ammonium chloride. Okay, so pKa of ammonium chloride is given as 9.25, molar mass is given 53.5, 25% weight by weight ammonium hydroxide solution is given, density 0.91. Like in the previous example, molar mass of ammonia is given as 7.03. So here we can take ammonium or ammonium hydroxide also we can take. So here if we take ammonium hydroxide, it is 35. So here instead of taking ammonia, we can take ammonium hydroxide. Is molar mass if given to us, that will be good for us. That is here if we see, it is 35 gram per mole. Okay, so instead of taking 17.03, you take 35 gram per mole. So answer at the end, we must have 0.8856 gram of ammonium chloride and 1.3 ml of 25% ammonium hydroxide solution. Make up the volume to 250 ml with distilled water to obtain a 0.1 molar ammonium hydroxide buffer at pH 9. So let us solve it now. You will use the Henderson-Hasselbalch equation, which is equal to pKa plus log of base by acid. So here pH is given as 9, pK is given as 9.25. So log of base by its conjugate acid and we will have 10 power minus 0.25 which equal to 0.568 ammonium hydroxide divided by ammonium chloride. So here ammonium hydroxide plus ammonium chloride will be are given as 0.1 molar, so total concentration. So if we take ammonium chloride as x, so ammonium hydroxide will be 0.5623x, and then x value will be equal to 0.06404, and ammonium hydroxide concentration will be equal to 0.036, that is 0.1 minus 0.06404. Okay, now for 250 ml it will be multiplying by 0.25 as we are doing earlier also, so it will be 0.01601 mole here, 0.00900 mole here. Now for ammonium chloride it is in solid, so simply we can multiply it by molecular weight, that is 53.5. here it is coming 0.5856 gram. Okay, now volume of concentrated ammonium hydroxide, that is we have to calculate 25% weight by weight. Density is given as 0.91 gram per ml. Okay, so mass of sodium ammonium hydroxide needed is equal to 0.00900 into molecular weight, that is 35, is equal to 0.315 gram. And since it's 25% solution, so to have 0.315 gram we have to take how much of the solution, that is we have to take 100 by 25 into 0.315, that is equal to 0.126 gram of ammonium hydroxide solution to be taken. But since it's liquid, we will have to divide by the density. 1.26 divided by 0.91 is equal to 1.39 ml. So your final answer will be 0.856 gram of ammonium chloride and 1.39 ml of 95% sodium hydroxide ammonium hydroxide to be taken to make up the volume to 250 ml with distilled water to obtain a 0.1 molar ammonium oxide buffer at pH 9. So here in this case also take full amount of ammonium chloride and slightly less, let's say you are taking 1.25 ml of ammonium 25% ammonium hydroxide solution initially, make up the volume to say initially 200 ml, adjust the pH using the remaining amount of ammonium hydroxide, and then finally make up the volume to 250 ml. You will have ammonium hydroxide buffer of strength 0.1 molar, pH 9. Okay, so this way we are calculating the concentration of ammonium hydroxide and ammonium chloride which is required to prepare 0.1 molar ammonium hydroxide solution. Okay, now let us do last numerical on preparation of tris HCl buffer. So what is tris? Tris is actually tris hydroxy methyl amino methane. Okay, so if I have to write the answer, that is structure. So if we see that methane is having 4 hydrogen group. Okay, now instead of hydrogen group at 3 hydrogen, if replaced by hydroxy methyl group, say here it is hydroxy methyl CS2H, here also it is hydroxy methyl CS2H, here also it is CS2OH. So this is hydroxy methyl, and one is aminomethane, that is it is called aminomethane. So this structure is of tris. Okay, and tris HCl is extensively used in biochemistry and molecular biology field, especially for maintaining the pH or the buffer for the maintaining of pH of solution containing nucleic acids. Okay, so this is mainly used in molecular biology and biochemistry field. Now here tris is base, here tris is base, and if tris is allowed to react with HCl, we will have tris HCl which will be acid. Okay, so here let us see how to solve this numerical, that we are giving prepare 500 ml of 0.5 molar tris HCl buffer, pH is 7.4, pK is 8, pK of tris is given as 8, molar mass of tris free base is equal to 1.21, and target buffer is 0.5 molar tris HCl, pH we have to given is 7.4, we have to, and volume is 500 ml. Okay, Now in the end we will must have the answer weigh 30.25 gram of trees dissolved in 200 to 250 ml water. Add 0.1998 mole HCl while stirring, and then dilute to 500 ml. Check pH, that is 7.4. This yields 0.50 molar tris HCl buffer at pH 7.4. Okay, now let us proceed for the calculations. Okay, so let us see how to arrive at this answer. So we will make use of Henderson-Hasselbalch equation, which is equal to pH equal to pK plus log base by acid. So here base is tris, and after reaction with HCl we have acid at tris HCl. So here your base by acid is equal to minus 0.6 and base by acid equal to 10 power minus 0.6, meaning that is equal to 0.2512. So from this, if we take the concentration of base as X, so acid as X, so we have concentration of base as 0.2512x, and since base plus acid is 0.5 molar total strength, so X will be equal to 0.39962 molar, and tris HCl acidic form will be equal to 0.39962 molar. Okay, so finally we from this, because total is 0.5, so tris free base will be equal to that is 0.5 minus 0.39962 molar, that is equal to 0.10038 molar. Okay, now since we want to prepare 500 ml, that is 0.5 liter, so total moles of both, that is tris that is required for both base as well as acid, that will be equal to 0.5 into 0.5, that is equal to 0.2500 mole, and mole of tris HCl that will be required from here, that is 0.39962 into 0.5 equal to 0.19981 mole, and moles of free tris, that is base, that is required is equal to 0.10038 into 0.5 equal to 0.05019 mole. Okay, so this way we are calculating the moles of tris HCl, free tris, and total moles. Okay, now we will convert it to the measurable amounts, how much tris to be taken and how much HCl to be taken, that we will now calculate. So for tris we have 0.2500 total tris to be taken, that is multiplied by molecular weight, that is 121 gram per mole. This is coming 30.25 gram, okay, or approximately 30.2 gram. Now so this is the total tris that is required, and how much of HCl is required to convert 0.11981 mole of tris to tris HCl, because we require how much HCl, 0.19981. so the total tris, from the total tris, how much HCl is required to have tris HCl, that is as 0.19981 mole. So this will be equal to 0.9981 mole HCl will be required, because we want this much tris will be used from this, and we will have 0.19981 mole HCl that is required. Now if we have with us one normal or 1 molar HCl ready, then volume will be equal to volume will required will be equal to 199.8 ml. Okay, of course if we are giving density also, then we can calculate by molecular weight and then by density, and then we can prepare. But if we have ready one normal HCl, we know that we are having, so how much ml of the one normal HCl to be taken, 199.8 ml, or around 200 ml of one normal HCl is required. Okay, so so finally we have reached to this answer, that we have to take 30.25 gram of tris. So you take a whole of this 30.25 gram tris, dissolve it in so we have to initially dissolve it in 250 ml water, then add 0.119 mole HCl while stirring, and check the pH, that it should be around 7.4, and then if it is not there, so you can adjust it. So as I told that initially you can take instead of taking 200 ml, maybe you take say 180 ml of one normal HCl, and then make up the volume. Say initially we have to prepare 500, initially you prepare 400 ml, and then adjust the pH to 7.4 using remaining HCl, and then you finally make up the volume to 250 ml. So finally you will have 250 ml. Oh sorry, here it is 500 ml. So instead of taking 400 ml you are taking, so to make up the volume to 500 ml, because 500 ml we have to prepare. And so in that we will have 500 ml of 0.1 molar tris HCl buffer, pH 7.4, pKa is equal to 8. So we have performed calculations for the preparation of buffer. So 5 numericals now we have solved: 2 on acetate buffer, 2 on ammonium hydroxide buffer, 1 on tris HCl buffer, and all about tris HCl buffer I have told you.